Welcome back to Precalculus 1. So today we're going to talk about the slope. I know you learned that in algebra, but we are going to talk about the slope in a context of precalculus, and we're going to use functions to compute the rate of change. So this concept will be heavily upgraded in Calculus 1 to a concept of slope of the tangent line, and the tangent line, it will measure the change, and that will be called the derivative eventually. So this lesson sets up a lot of important things for Calculus 1. But there is also a lot of pre-calculus type of calculations and concepts that we can cover with this. We can model, we can do some word problems. So we're going to take a look at all of that stuff right now in this section. So we're first going to start with the good old idea that the slope was labeled by lowercase m, and from algebra we know that's y2 minus y1 over x2 minus x1, which is technically change in y divided by change in x. So these are all the variables that are involved. And if you think about the slope, you draw any type of line, you can pick 2 points on that line and then just draw these lines. So if you think about these 2 points, you call this one, let's say, x2, y2, and this one x1, y1. It really doesn't matter which one is which. Then you can clearly see that this height over here, so the top point has the y2 as a value, and the bottom point here at the right angle has the y1 as the y value. So if this is y2 and this is y1, their difference is delta y. And that's what it's called a change in y, because you go from y1, which is on the bottom, all the way up. And then there is a difference there. Now, this point on the x-axis would be x2, and this one would be x1. And if you look at these two like this will be your delta x, which is change in x. You changed from one x to another x in terms of values, in terms of numbers. So understanding what the slope is, literally you ski down the slope, you hike up the slope, and so on. The slope measures how steep the line goes, either up or down. And we actually have a numerical value to assign to each one of these slopes and measure it. So we can compute the slope in algebra. If you have 2 points given, you plug everything into the formula that you see, and you just compute. Slopes can be positive, negative, 0 for horizontal lines, and infinite slopes for vertical lines. All of that was covered last class, or reviewed last class. But what we want to do today in this section is to upgrade this idea, and we are upgrading this idea by replacing y's with functions. So we are going to calculate the rate of change on the function by using function to compute the y values. So knowing that y is equal to f of x, we can take our y2 minus y1 divided by x2 minus x1, and we can change that into f of x2 minus f of x1 divided by x2 minus x1. So as you can see now, all I need is the input x. I don't have to be provided with y's, because y's I can compute. If I have a function, then I can compute the y's by plugging x's into the function. So we are exploring this idea. Here, I'll bring some purple. You happy now? Well, thank you. So this is what we are looking for, and we're going to say rate of change, right, for the So let's see. Graph-wise, remember that you need to understand a little bit of theory before we actually do problems. So graph-wise, I can pick up so what would be the equation for this function? Anyone knows?
F of x equal to x squared plus 2.
Awesome. Yes. And that's exactly what we're going to learn after this lesson. So you know it already. So y equals x squared plus 2. So we have the U-shaped parabola, which is x squared, and it's moved up 2 units. So it's plus 2. So let's say that I want to know what is the rate of change between x1 equals 0 to x2 equals, let's say, 2. Well, I can compute the y values quickly. So rate of change is going to be equal to, and we'll say, f of 2 minus f of 0 divided by 2 minus 0. So observe that the x1 and x2 are given to you because you need to know that destination, right? But then y coordinates are not given, and you can compute them because y equals f of x. And if you know x1 and x2, and you know f of x, then you can compute y1 and y2. So we have, since the function is x squared, we're going to have 2 squared plus 2 minus 0 squared plus 2 divided by 2 minus 0 is 2. So the first one is 2 squared plus 2 is 6 minus 2 divided by 2, and the answer is 4 over 2, which is 2. Does any of this make sense? Now, how is this different in algebra? In algebra, I would provide you with the point 0, 2, and then 2, 6, and ask you to find the slope. But here, I'm only providing you with x1 and x2, and you can use the function to find your own y values at those points, and you're still computing the slope. So try not to make a big deal out of this, all right? Compute, and you're done. So we are just technically redefining, the way we write the slope. We are redefining the way we write the slope. We have now, instead of y2 minus y1, we have f of x2 minus f of x1 divided by x2 minus x1. I'm trying to see if we can, trying to switch to the homework section so we can actually do a few of these examples. are no actually. Yeah, I think I only have 3 examples. Wow. Okay, so let's take a look at problem 30. So they only have 3 examples in the textbook on this one. All of these are word problems, and all you need to do is to pick up the values, and the functions are given, and just plug, right? So they say that the function f of x equals 1.1 x cubed minus 35x squared plus 264x plus 557 models the number of discharges in U.S. military under Don't Ask, Don't Tell, X years after 1994. Use this model to solve the problem. So we start counting time. So t is equal to 0, actually x equals to 0 in 1994. So that's where the data starts. So what's the 2000? How much is x for 2000? 6. Between 2000 and 1994 is 6 years. So x is equal to 6 for 2000, and so on. All right, so let's see what they want us to do. Find the average rate of change rounded to the nearest whole number from 2001 to 2006. So find rate of change, find rate of change from 2001 to 2006. Well, we have everything we need. If I know that x equals to 0 in 1994, how much is x in the year 2001? 7. So x1 equals 7. Awesome. And how much is it in 2006 for x2? 12. 6 and 6 is 12. Now, I know that a bunch of you will not ask, and you're still confused with this. What happened here? We are rescaling the problem. I don't really want to drag. I could, but I don't want to drag 1994 and 2001, and right. So what we do is we rescale that. If I'm interested in years 2000 and on, right? In this case, they were interested in years 1994 and on. Maybe this is the first time, 1994, when concept like this was even discussed. It did not exist before that. So you set that as the beginning of time. So 1994 is the beginning of time. And then you scale all other years according to this. If in 1994 the time was 0, which is when everything begins, then in 2001 it's 7 because it's 7 years after, right? The beginning is 1994, 2001 is 7 years away, 2006 is 12 years away from 1994. So I have that conversion, and now I have x1 and x2. I also have function. So what's the rate of change? All we need to do is to plug these values in and compute. So I have the rate of change is f of 12 minus f of 7 divided by 12 minus 7. Now, guys, it's going to be a hell of a calculation, right? Because the numbers are awesome. But then they say, oh, that's it, to the nearest whole number. All right, so let's go. So all of this is equal to, put the division line there, and then we plug in 12. So it's going to be 1.1 times 12 cubed minus 35 12 squared plus 264 times 12 plus 557 minus open parenthesis, and we repeat the whole thing for sevens. So 1.1 times 7 cubed minus 35 times 7 squared plus, see, it doesn't fit, 264 times 7 plus 557. Everything divided by 5. Equal to? And now you compute this. So I'm going to do this on my calculator quickly. I'm using TI-83 Plus. So you can use any calculator that you want. Exams, no graphing calculators.
What about the one on the phone?
Yeah, you can use the phone. Not on the test, though. But yeah. Yeah. That's. I mean, you can do both. What was it? 1.1 x cubed minus 35x squared plus 264x plus 557 Is it 12 and 7? Yeah. Negative 481.5, they say round to the nearest whole number, so I will have to round this to negative 482. Now we are talking about discharges from military for homosexuality. That's problem 30, 31 and 30, I think. No, 29 and 30. And we see this number, negative 482. Now that's the reason why they asked us to round to whole number. That should be common sense if you're counting people or rabbits or something, doesn't matter what it is, has to be a whole unit. You can't be working on a population of rabbits and get 517.8 rabbits. Right? So no decimal numbers for these kind of calculations. You have to have a whole unit, whether it's a person or a tree or whatever. All right, so now we know what we're talking about. The problem was the number of discharges from military due to homosexuality. That's one of the 8 problems they have in the textbook. Well, actually, 2 problems together, same text, just different numbers. So now, what does this number mean? What is this negative 482? Yes?
Did you divide it by the...
Oh, I didn't divide by 5. I forgot to divide by 5. So this is 481.5. So negative 96.3, so negative 96.3, and we are looking into negative 96 just negative 96. Good catch. Nice.
I was like,
Yeah, divided by 5, yes. So now, can you interpret this? Because if you solve the word problem and you have no clue what it means and what it is, then what good is solving the problem? So what do you think, guys? What is this negative 96? Yes?
That's the, how many people, so it's dropping 96 people from getting discharged per year.
Okay, yes.
For being homosexual because of the Jonas Hotel.
Yes.
is that per year? Because it would be per year, or it would be from the span of 2001 to 2006.
It's for the entire, for that span. So it's not per year, it's for the entire span.
Would it not be an average?
Yeah, the average rate.
It's the average, so it's per year, isn't it?
Yeah.
Okay.
So, wait. First of all, they say the average rate of change. Yes, the average rate of change. So the rate of change is, so let's hold off for a second. What do we have over here? We have 12 minus 7. How many years are in there? 5. So that's that 5 there. Now this 5 is dividing the change of how many people were discharged. Over the course of 5 years, 481.5 people were discharged. And then when you divide that by 5, you get the average per year. So this answer here, now the true data is that if you look at each year individually, they have different numbers, but it's going down. This number averages that and says if it was the same amount discharged every year. So this is how many people were discharged, 481.5, right? And then divided by 5 gives us 96.3, which is 96. So you would claim that 96 are discharged per year. And then you can try different years to see how much were discharged different times. So per year, well, maybe I should write. Yeah. So it's negative 96. Now, what is the significance of a negative? Yes? They're losing, yes. So it's getting smaller, right? There will be a negative slope. So if you are to graph this, loosely, it's going to look like that. So negative slope. All right? Now, this concept is also known as the slope of the secant line. In Greek letter, the secant means to cut. And you know that if I drew the picture earlier, but here's another one. So you want this point and that point. To calculate the average rate of change, you calculate the slope of this line. The slope of this line is m, but we also know as the slope of the secant line. So some problems might say find the slope of the secant line. Well, that's actually just the slope that you know how to get. Except this time around you have to plug in x and y. Sorry, x to get y. Good. I wish I had more examples in the textbook. I don't. It's just maybe we can do another one. I don't know. Because both of these examples that are given here are for discharges are on the same function and the same, just they change the input values. There's another problem that says percentage of total spending in the United States on food and healthcare. So that's another, it has two problems in there, 27 and 28. And they both, let's take a look at one of these. So how about we take a look also at 28, so you have another example. Oh, but they don't give you the function. So we're going to do a little bit of the Excel work. So in this class, you know you have labs. Labs will all have the most important problem, or the most important two problems at the end. Those will be the application problems. And for most of those, you will have to use Excel or the calculator, but Excel is better and faster, to find the equation of the line, to find a function which is going to be used for you to model the problem and calculate the stuff that is needed to be calculated. So let's take a look at the data first. So in 1950, Americans spent 3% of their budget on healthcare. This has increased in the average rate of approximately 0.22% per year since then. So in 1950s. They say, find a linear function in a slope-intercept form that models the given description. Each function should model the percentage and total spending P of X by Americans X years after 1950. So we are starting with 1950, and we're going to call that X equals 0 because that is our initial time. This is where everything begins, 1950. So we're going to call that X equals to 0. And then we're going to take a look at the rest. So Americans spend the budget on healthcare. So we're going to take a look at the healthcare data. I'll just show real quick how this looks like in the book. So you have a healthcare data given here. And you see that, look, in 2010, the healthcare is 16% out of everything you earn per paycheck. So 16% goes to daycare. 2010, where in 1950 only 3% went. Now, healthcare is much more expensive today because of all of the fancy equipment, fancy technology that is there to extend. And we know that overall, right, since we have a longer lifespan today than in 1950, we know that all of that machinery and medication, everything actually helps. So people live longer. So obviously there is a higher cost associated with it because, you know, in 1950, there wasn't that kind of technology available. So now, we are going to normalize this data. So we have for 1950, we also have a data point for 1970. So for 1950, it was 3%. For 1970, X is 20, right? Because it's 20 years after 50. I know. I want you to figure it out. I am writing here. Everyone, look. It's going to literally be there for 2 seconds and it's going to go away. So, ready? Ready? There you go. So, 1950, X is 0, 3%. 1970, X is 20, 7%. And then I have another 2 data points. 1999. No, 1990, sorry. What's the X value for it? 40, and the data says 13%, very good. And we have the last 2010. What's the X for it? 60, and the percentage is 16%. So, the beginning of time The beginning of everything regarding healthcare starts in 1950, so we're going to call that x equals 0. And 3% was assigned to that. So these are your x values, and this is your y value. So now, in 1970, that's 20 years later, so x is 20, you have 7% as the output. Input, 1990, which is 40 years away from 1950, 13% output, and then 2010, 60 years later, is 16%. So now that we have all of this information, the chart that you have should look like this. And we are only going to use x's and their outputs, 3, 7, 13, and 16. We don't use percent. That's like a, yes?
You said the percentages are your y values?
Yes, because they were listed. If you look at the graph that was provided, you would find all of the percentages. See how it switched? The percentages are on the y-axis, and the time is on x. Now, they give us two sets of data on the same, so these are two separate graphs, right? But they are on the same graph paper. All right, so now what we're going to do, guys, is we're going to find the line of the best fit. And the way to do that is going to be either using Excel or using the calculator. Those are the two that you should kind of learn in class. And then if you can come up with anything else, find some kind of other software that you like to use and figure out, go ahead, right? Life is just about the choice, right? You make the choice. So let's see how is this done on Excel, because it's the fastest and easiest way to do this. So I'm going to quickly start Excel. And here we go. So we have Excel. We can go anywhere. I'm just going to go here, so you know, I'll go a little bit in because I need to make sure that the stream is catching everything. So I'm going to start here. It really doesn't matter where you start. You type all of the x values going down. So we have 0. Underneath we have 20. Then we have 40. Then we have 60. Then come up in the next column. We had 3. Then we had 7. Then we have 13. And then we have 16. You will have to use this for your labs and projects. You must know this skill. So you open up Excel, and in any squares anywhere on it, doesn't matter where, try to keep it to the left as much as you can. You can literally do it right here with these, you know. But later, if you want to format, it's going to be, you know, paid to get to the title and stuff. So, you know, but somewhere there. We put all of the x's down, all of the y's down, making sure they correspond, and you need to have the same amount of rows and columns right there. So now when you have all of this, the rest is very simple. Now all of this is on stream, so you can go and review it as many times as you need to learn this skill. You will need this, guys. You select the data using the mouse. You click on the first cell and just drag while pressed the button, right, to select all, in this case, 8 numbers. And then you will go up there to Insert. And once you click on Insert, you will find over here all these graphs. You are looking for the one with dots called Scatter. So you will click on the little arrow there. It will open. And the first one on top left is the basic scatter plot. You don't want this connected with any lines. You just want the most basic plot of scatter data, which means it will just give you dots. See? Because if you connect this with any of the other ones, it will actually connect these dots for you, but that's not going to be a straight line. It's just going to be a zigzag line, and that's useless to us. So we want just the data to appear in its pure form. So you see that 0 is 3% there. 20 is 7% because this is 6 and 8, right? It's right in the middle for 7. 40, you have 13, again in the middle, between 12 and 14. And for 60, you have exactly 16%. So this is your data, and literally something like this should take about a minute of your life. And now here is how you find the equation. The best fit of the equation. You right-click on any of the dots. Pick one dot, doesn't matter which one, and right-click on it. It will say the second to last, add trend line. Add trend line. So you click there, and it opens the new menu on the right. We are going to learn all of these in this class. You will learn about exponential functions in chapter 3, linear and polynomial functions in chapter 2, logarithmic, again, chapter 3. Power is the same thing as up there, and moving average, we don't do that one. Now, we want the linear line. Since linear is selected, it already populated the best fit line through the data. Observe that this line hit one point and missed all of the other ones, but this is the best line, the fit that you can get, so that the points that were missed are the shortest possible distance away from the actual line. There's a whole statistical method of how is this actually done by hand. Should take a few hours. But the computer does this very quickly, and you are able to pick any of these. So you will be picking, obviously, between the first 4, you will be picking for all of your labs and for your project. You will be using this so that you don't have to mess with the calculator. It takes forever. And you will go all the way on the bottom. The second to last says display equation. So you display equation, it will show the equation, and that equation you can move anywhere if you can't see it very well. So now we use the software. We typed in the data points. We selected everything. We click on an insert scatter plot. Right-click on any of the data points. Once you have that, you click on add trend line. Select which one you need. In our case, linear. We need the linear line. And check off display equation so you can see the equation. Once all of this stuff is done, you can X out from the side menu, because maybe you want to format and do other things, so you need more workspace. You can leave it there, doesn't bother you. But there's the graph, right? That's the graph, and here is the line of the best fit through the data, and we only had four points given. And here is the equation of the line, which is calculated. You see a slope there, and you also see the y-intercept. Now, what's the power of mathematics? The power of mathematics is that once you have a mathematical model, you can use that mathematical model to predict the future. That's how we know what weather is going to be, tomorrow or so on. There are very sophisticated mathematical weather models. Those are the systems of partial differential equations that are coupled. And there are supercomputers that are computing those at all times. You feed a lot of data in terms of the pressure and temperature and all of that stuff. And these computers are cranking data all the time, telling us mathematically how the weather is going to look like. Now, anytime when something is wrong, people go and adjust the models and make sure that the bugs and things are fixed. So today, it was pretty much, it's pretty easy to say what the weather will be just looking at the model. So in same sense here, you guys can, let me just get something. You can predict what's going to be in the future, right, for these. Okay, so 2016, right, today. So let's say 2020. 2020, since this is 2010, 2020 must be at 70. You can extend, so you will put 70 into this equation, and it will tell you what percentage of the paycheck. Now, this model is obviously not the greatest model in the world, because if you wait sufficiently enough, it's going to rise up to 100% of your paycheck to be healthcare, and we know that can't be. So certain mathematical models are good for a short period of time, and then later on they're not good, right? That's the reason why you collect more data, and then when data starts curving, you start using the different functions, which is the reason why we have exponential, logarithmic, square root functions, and everything else, right? Because not every single problem out there, every single concept is linear. I also wanted to show something real quick, because this is, I believe, the very important. Let's see if this is a good one. Yeah, this is. So this is how I used to do weather, and now we have mathematical models. See, that's a weather stone. I don't know if you're familiar with this, and it has, you know, in the background what it means. So I don't know if you saw this before. If the stone is wet, it's raining, right? If the stone is dry, it's not raining. It's very, very simple, right? Shadow on the ground means it's sunny. White on the top means it's snowing. Can't see the stone, it's foggy. Swinging stone means it's windy. Stone jumping up and down is earthquake. And stone gone, tornado. Or someone stole the stone, but you can just get a new one. Why would you bother stealing a weather stone? It's an important piece of. So yeah, that's how it used to be in the good old days. Or you would go and ask the natives, right? They know, because they have the bones and things, like all that stuff, and they know immediately what's happening. But now we actually have the weather models, which are very accurate, so we don't actually have to do any of that stuff. Now, I was actually thinking of building one of these actually at my place. It would be very useful. But then one student said, well, you can just look at your car in front. It does the same thing, right? Which is actually a problem for snow, because you can't tell if the car is white. And that's the only issue. So if you have a non-white car, it would work perfectly. But also, if the car is gone, then there might be something else. It's not just all right, great. So that takes care of the weather models and other models. So for 1.5, we are done with 1.5. We did 2 out of 4 examples in the textbook. So what are we dealing with? We are dealing with a standard equation for the slope that you learned in algebra, y2 minus y1. Let me switch back over here so you can all see it. Oh, I did not write the information here. So I'll just say use Excel to get, and our model was y equals 0.22 something, something, something. 225x plus 3. 225x plus 3, so x plus 3. And this is the years since 1950. And this would be the percentage of the paycheck that goes towards the health care. So I just wrote this one line here with the answer that we got from Excel. And now we can use the model. So this is the answer. They asked for the model, so there it is. And now you can use this to predict the future. So plug in, I don't know, as I said, plug in 70, and you can predict how much you're going to pay out a paycheck for. So that's in 4 years. So some of you might be working full time and worrying about those things already in 4 years. Yeah, welcome back with me. So that's 1.5. What we are doing, and here is one more time just to show it, we are taking our basic algebra slope formula and rewriting it. Instead of y's, we are putting f of x there, and we will be computing at x1 and x2, which is the changing from x1 to x2, whether it's years, whether it's height, whether it's whatever, is changing from one number to another. And we are calling it the rate of change. The answer that you get will be per year, per minute, per something, because it is the average rate that is computed at the end. So that takes care of the section 1.5. I'm going to turn the stream off and then restart for the new lesson. We're going to do 1.6